Welcome to our class notes of acids and bases. This is part the first of these notes. This video is approximately 35 minutes long. When you're done watching it, you can watch part 2. So in part 1 here, we're going to discuss what acids and bases actually are and how we identify them and a few other basic topics with them. In part 2, we will get into pH and calculations involving them and titrations and such. So what are acids and bases? There are actually two main ways of defining acids and bases, different models or definitions of acids and bases. The first of those is called the arrhenius model of acids and bases. The other is known as the Bronsted Lowry model of acids and bases. We're going to talk about both of these models in depth over the next couple of minutes. One is better than the other for certain situations. One is better than the other for other situations. They both have their good points and their bad points, and so we're going to talk about that. So buckle up. We're going to have fun. So the first model of acids and bases is the Arrhenius model. It is named after a Swedish chemist, Svante Arrhenius. He created this model for acids and bases around 1883. And in his model, his definition, the way he described acids and bases, was that he defined an acid as a substance that contains hydrogen and ionizes to produce hydrogen ions in aqueous solution. So we have an example here of HCl, or hydrogen chloride gas, produces H plus ions. So there we go. That's our H plus, our hydrogen ion, in aqueous solution. AQ means aqueous, and if you remember from our solutions unit, aqueous means dissolved in water. So, Arrhenius defined any acid as a substance that contains hydrogen and will produce hydrogen ions when you dissolve it in water. That's what makes something an acid. An Arrhenius base is a substance that contains a hydroxide group and dissociates to produce hydroxide ion in aqueous solution. Again, dissociate means ionizes as well. So a base is anything that contains a hydroxide group. A hydroxide is OH, so sodium hydroxide will produce sodium ions and hydroxide ions in aqueous solution when it is dissolved in water. So it makes it a base because it produces hydroxide ions, I should say, when you dissolve it in water. So that's the Arrhenius model, acids and bases. Arrhenius acids produce or contain hydrogen ions and produce hydrogen ions. An Arrhenius base contains hydroxide and produces hydroxide ions in solution. Now, one of the problems with the Arrhenius model is that with acids, you have to have a hydrogen, and with bases, you have to have a hydroxide. Well, it was found out that there are some things that act like acids and act like bases, do all the same thing, are essentially acids and bases, that don't necessarily have those things in their compound, specifically hydroxide. There are many bases that do not actually have hydroxide as part of their chemical compound, but they are still bases. And that led to the Bronsted Lowry model of the acid bases. Bronsted Lowry model is called Bronsted Lowry. It was created by a Danish chemist named Bronsted and an English chemist named Lowry. Those are their last names. I don't know their first names. Proposed a model that focuses on the hydrogen ion instead of hydrogen and hydroxide. They just look at the hydrogen ion itself. So they defined an acid as a hydrogen ion donor, something that will give up a hydrogen ion when you put it in solution. When you dissolve it in water, it will produce or give up hydrogen ions, H+. And they defined a base as a hydrogen ion acceptor, something that will take those hydrogen ions out of solution once they have been donated. So an acid donates hydrogen ions, a base accepts hydrogen ions. Now this was helpful because it helped explain why certain bases that do not have hydroxide still acted as a base, because they may have not had hydroxide, but they would accept the hydrogens that were being produced by acids. So for example, something like, let's say ammonia, which is NH3, it does not have a hydrogen or a hydroxide group like the arrhenius model would say, but it will actually take, if I have an H plus ion in solution, they will actually combine and make NH4. So this will accept a hydrogen ion, and therefore it acts as a base even though it does not have a hydroxide group like the arrhenius model says. So now we're going to move on and talk about some characteristics of acids and bases and how we can identify them. These characteristics, of course, are not completely 100% always true, but they are generally effective for all of them. And some of these things you wouldn't want to know one way or the other. For example, acids, the first characteristic of an acid is that they are substances that taste sour. Now, obviously, you're not going to want to taste every single acid you come across, but those that we can taste, that we do taste, they taste sour, i.e. lemon juice. It's pretty sour. Vinegar is pretty sour. These are things that are acids that, they taste sour. I don't know how else to say that. Their chemical formulas pretty much always begin with hydrogen. That's one good thing about the arrhenius model, is it says that it has hydrogen, and in order to have the ability to donate a hydrogen ion the way the Bronsted Lowry model says, in order to donate a hydrogen ion, you have to have a hydrogen ion, and hydrogen being a positive will pretty much always be first. When it's in an ionic compound that would then dissociate into liquid, it has to be the first one, so acids will pretty much always begin with hydrogen. Acids are found in many foods and drinks. Lots of the stuff that we come across are acids. If you watch enough cooking channel or cooking shows, you'll actually hear them talk about the acidity of certain things, helping with the way that they taste good and all that fun stuff. Acids can be identified as things that will turn blue litmus paper red, as you saw in the little activity that we did. You take blue litmus paper, you put it in an acid, it turns red, it's nice and pretty, it's all fun, yay! Now, acids have a pH between 0 and 6.9. We'll talk more about pH here in a little bit, but pH is a measure of the acidity or basicity of something, and the pH of acids is anything from 0 up to 6.9. Acids are corrosive, and corrosive simply means that it will cause things to degrade or oxidize or corrode, fall apart, come apart. We typically talk about this as something that they eat through things, and you actually see that that's one of the things that they show you in this thing about acids, that there's dangers. You drip it on there and it eats it away. It's corrosive. That's the eating away of things. They form hydrogen ions or H3O plus ions in solution. We will talk about this here in just a minute. H plus is, of course, hydrogen ions. This H3O plus is called hydronium, and it happens whenever H plus is in water, which is what happens in acids. We'll talk about hydronium here in a few minutes more in depth. But these are the general characteristics of acids. Taste sour, begin with hydrogen, found in many foods and drinks. They turn blue litmus paper red. Their pH between 0 and 6.9. They're corrosive, and they form either hydrogen ions, also known as hydronium ions, in solution. So now let's talk about the characteristics of bases. Bases are not really the opposite of acids, but sometimes they're thought of as being the opposite to acids. They're kind of like the nemesis, the enemy of acids, I guess we should say. They tend to taste bitter, so they're not necessarily sour, they're bitter. That's a slightly different flavor. Some people get confused by that, but bitter is slightly different. They tend to end in OH, but not always. As we just learned from the Bronsted Lowry model, bases do not have to end in hydroxide. They tend to. Most compounds that do end with an OH are bases, but not all, and not all bases end with OH. So it takes a little bit of practice to figure this out. As we saw from the lab, they turn red litmus paper blue. So a base turns it blue. That's a fun way to remember it. And so there you go. That's red litmus paper turning blue. The pH of a base is between 7.1 and 14. So the pH scale goes from 0 to 14. We'll talk about the pH scale a little bit more in a few minutes, but again, that's a measure of how basic or acidic something is. Bases tend to be found in a lot of cleaning products. There are a number of foods that also have bases in them that are also basic, but our foods tend to be a little more on the acidic side, and bases tend to be used in cleaning products a whole lot more because of some of the properties of bases. They tend to be slippery, like soap, for example. It is rather slippery, so it is a base. Hence, a lot of cleaning products have that soapy feel to them because they are basic, and bases tend to feel slippery. They are also corrosive, and that is a common misconception, is that acids are corrosive and bases are different than acids, so they're not corrosive, and that's not actually true. You can actually have a very corrosive material, something that will eat through, quote-unquote, something else that is a base and not an acid. So you don't have to have an acid to eat through something. But as we learned from the arrhenius model, they will form OH ions in solution. They're hydrogen ion acceptors, as the Bronsted Lowry model tells us, and so that will often cause them to form OH minus ions in solution, and that should be pretty obvious. If they contain a hydroxide group, when they dissolve, they're going to form a hydroxide ion. Boom, hydroxide. So looking back at the arrhenius model of acids and bases, since we talk about them in terms of hydrogen ions, or H+, and hydroxide ions, OH-, let's talk about how they relate to each other. We basically have three different types of solutions. You have neutral, you have acid, and you have base. Now, a neutral substance is going to be something that whenever it's dissolved in water, the number of hydrogen ions and the number of hydroxide ions are equal to each other, so it is balanced. That doesn't mean it does not have hydrogen or does not have hydroxide. A neutral substance can have both hydrogen and hydroxide. What this means is that you have equal amounts of them and they're equally balanced, so it is neutral. It is neither heavy on the hydrogen nor is it heavy on the hydroxide. It's balanced, neutral. An acid, on the other hand, is something where you have more hydrogen than you do hydroxide. So acids can have hydroxide in the solution, they just have more hydrogen ions than they do hydroxide ions, and so therefore the scale is tipped a little bit towards the side of the acid. It is no longer balanced and neutral, it is now slightly acidic because there are more hydrogen ions than hydroxide ions. And as it would imply, that would mean that something that is basic has fewer hydrogen ions or more hydroxide ions than it does hydrogen ions, making it balance and lean to the other side closer towards the base. And so these are your three basic situations of neutral, acidic, or basic. So if you wanted to adjust your solution, if I increase the amount of hydrogen ions, it's going to mean you're going to have less hydroxide ions, and it's going to become more acidic, and your pH is going to go down. More acidic means your pH is lowering. And if I take and decrease the amount of hydrogen ions, it's going to increase the amount of hydroxide ions, and it's going to become more basic. And so your pH is going to increase. Again, a decreasing pH is more acidic, and increasing pH is more basic. So you can actually have an acid that is turning more basic by something that, say, it has a pH of 2, and I add stuff to it to make the pH climb up towards 7. It's until it reaches 7, it's still acidic. It's just becoming less acidic, so it's more basic as I increase the hydroxide concentration. That's the principle of something we're going to talk about later called titrations. And again, a lot of this has to do with whether or not something is acidic or basic or neutral. And there is one compound that is the most important compound in all of this, and it is one that is, by its own merits, neutral. And that is water. Water is neither an acid nor a base. So H2O can also be written as HOH. So we have 2 hydrogens, 1 oxygen. This still has 2 hydrogens, 1 oxygen. So you can write it as hydrogen hydroxide. So you'll see that it has both an H and it has an OH. So it could be either an acid or a base. That HOH will actually break apart into H plus ions and OH minus ions. It doesn't do that completely, but it does do it partially. And when this happens, the free hydrogen, this extra hydrogen ion here, is going to bond with one of these water molecules that's sitting around. So some of these molecules are going to separate into hydrogen ions and hydroxide ions, and you're going to have a free hydrogen ion that's going to combine with a normal water molecule to create an H3O+. We call that hydronium. Hydronium is the result of having hydrogen ions in water. They will pretty much always do this. The hydrogen ions will combine with water molecules to form H3O+. Because of that, H plus and H3O plus are used interchangeably. Sometimes we talk about hydrogen ions, sometimes we'll talk about hydronium ions. As far as this is concerned, these are the same thing. If I ask you for the hydrogen ion concentration, or if I tell you the hydronium ion concentration, it's the same thing either way. They're used interchangeably. Because hydronium ion and hydrogen ion are used interchangeably, we talk about something called the self-ionization of water. And what that basically means is that you have 2 water molecules that will react to form a hydronium ion, H3O, and a hydroxide ion. So you're going to end up with a situation very similar to this. We have a water molecule, we have a water molecule. One of these water molecules is going to give up one of its hydrogens, which is going to come over here to the other one. That's what the self-ionization is. And one of these molecules is going to become a hydronium, and one of them is going to become a hydroxide. And so H2O yields H plus and OH minus. And this is one of the principal reasons why water is a neutral substance, because unless you have an odd number of molecules, which of course how would you ever know if you have an odd number of actual molecules, your water is always going to separate into hydronium and hydroxide. It's going to do that in equal amounts. So you will always have an equal amount of H plus as you do OH minus, and if they're always equal, then it will always be neutral. But one of these things about water doing this is water is not the only thing that ionizes. All acids and bases ionize when you put them in water. And it's something about that ionization that helps us determine some very important concepts about acids and bases. So let's talk about this ionization. The Bronsted Lowry model shows us that if an acid or base is strong, it's based on its ionization. Whether or not an acid or a base is a strong acid or a strong base has to do with how well it ionizes when you put it in water. Some compounds will ionize completely, some compounds only ionize a little bit, and so that's the difference between a strong acid and a strong base, and a weak acid and a weak base. A strong acid is one that will completely ionize. So if I put a strong acid in water, it will completely, 100%, ionize into hydrogen ions and its other subsequent thing. For example, hydrogen chloride, when you put it in water, is going to completely break apart into H plus and Cl minus. It's going to completely ionize into hydrogen ions and chlorine ions. A weak acid, on the other hand, only partially ionizes. It does not completely ionize when you put it in solution. So something like acetic acid, otherwise known as vinegar, when I put it in water, only some of it is going to ionize. We show that by showing a double arrow here. And so some of it will form hydronium ions, or H+, and some of it is going to form the acetate ion, but not completely. In fact, only about 10% or less than 10% of the acetate ions will actually dissociate and ionize when you put it in solution. That's the main difference between a strong acid and a weak acid, is how much it ionizes when you put it in solution. So we need to talk a little bit about this common misconception about strength and concentration. When we talked about concentration in our solutions unit, concentration was how much solute was dissolved in the solvent. Well, with acids and bases, the solvent is water. So when we're talking about how much solute is dissolved, that's our acid or our base. And the strength of an acid or a base is completely independent of its concentration. Strength is defined by how completely it ionizes. If I have 100% ionization, it is a strong acid. If I have less than 10% ionization, it is a weak acid. How much it ionizes is its strength. So, strong completely or almost completely ionizes. Weak only ionizes partially, whereas concentration is how much solute is dissolved in your solution. A concentrated amount is going to have a lot of acid or base in water, and a dilute amount will have only a little acid or base in water. You can have a concentrated weak acid, and you can have a diluted strong acid. It's all a matter of how much you have dissolved and whether or not it completely ionizes or only partially ionizes. So try not to get confused with strength and concentration. Hydrogen chloride or hydrochloric acid is a strong acid. Even if it is very diluted, it's still considered a strong acid. Now, concentrated acid is going to be much more hazardous to you and have a much greater effect than a dilute acid, but the strength is determined by how it ionizes, not by how much of it you have. So for example, 12 molar hydrochloric acid is a strong acid with a high concentration. In fact, 12 molar is about as much the highest concentration you can get because of the solubility of HCl in water. 12 moles per liter is about the maximum you can get. And so you have a strong concentrated solution. If I were to add 6 liters of water to this solution, I would now still have 12 moles, but I'd have 6 liters instead of 1, so 12 divided by 6, that would drop it from 12 molar down to 2 molar. So what's going to happen to the solution? It's still a strong acid because it's still HCl. It still ionizes completely, but now that it is not as concentrated, it is a dilute solution. So just because it is diluted does not mean it's not still a strong acid. Another example is vinegar. Vinegar has acetic acid in it. That's essentially what it is. It's 3% acetic acid, which is weak in low concentration, or low concentration meaning when it's diluted. So vinegar is a weak acid. 12 molar acetic acid is still weak because it only ionizes partially, but it would be very concentrated because there's a lot of acid dissolved in the water, even though it's only partially ionized. Because in order for it to act like an acid, it has to be able to produce those hydrogen ions. So if it only partially hydrogen ionizes, it doesn't matter how much you dissolve in there. If only 10% of it is going to ionize, then you're not going to get the full effect of the H+, and so it's going to be considered a weak acid. So let's talk a little bit more about strong acids. Since strong acids are completely ionized, they're going to produce the maximum number of ions possible. They completely ionize, so the most ions possible are going to be formed, which makes acids good conductors. Strong acids good conductors. They have lots of ions, and if you remember from our solutions unit, that means they are electrolytes, because they conduct electricity when they are dissolved in water. This is one of the reasons why we use strong acid like sulfuric acid in car batteries. They conduct electricity, they allow electrons to move. That's a really good thing. We're not going to get into electrochemistry in this class because it's really complicated, but there you go. Strong acids are good electrolytes and therefore good conductors. Now when we write the equation for a strong acid, we have to remember that the reaction only goes in one direction. And what that means is that when you put a strong acid in water, it is going to completely ionize and go all in one direction, and we represent that by using an arrow in one direction, as you saw me do earlier. The way that we normally do an arrow for a chemical reaction is simply one arrow pointing to the right. Weak acids, on the other hand, as we've already discussed, ionize only partially in dilute aqueous solutions, and therefore they produce fewer ions, so they're rather poor conductors. They'll still produce a little bit of ions, and so they're still going to conduct electricity a little bit, but they're not going to do it nearly as well as a strong acid will. That's why you don't want to try and use vinegar in your car battery. You want to use sulfuric acid, because it's a rather strong acid. When we write the equations for weak acids, that move in both directions until equilibrium is reached, which means some of the ions are going to come apart into H+ ions and the constituent ions. So let's say we have acetic acid again. Some of it's going to come apart into H+ and acetate ions, but then not all of it. And so some of those acetate ions are going to combine back with H+ ions and form the hydrogen acetate, and back and forth. So we represent that with an arrow in both directions, typically drawn like this, to show that sometimes the hydrogen ions are going to move this way and sometimes it's going to go this way, because it's going back and forth until you have equilibrium reached. We call that a weak acid. It goes back and forth both directions. Now I keep saying the hydrogen ion and the other thing. So let's talk about what that other thing is called. It's called a conjugate acid conjugate base pair. So what is a conjugate acid? Well, the conjugate acid is the species produced when a base accepts a hydrogen ion to form an acid. The conjugate base, by definition, is the species that results when an acid donates a hydrogen ion to form a base. So what exactly does that mean? Most confusing thing here is when we talk about species. That means to me the thing, the item, the substance, the chemical that results, that is produced. That's what we mean by species. So in every reaction we have an acid, we have a base, and then we also have the conjugate acid and the conjugate base. And again, these definitions can be a little confusing. We'll hash it out here in a second. But the conjugate acid is produced from the base, and the conjugate base is produced from the acid. So every acid and base are conjugate acid-base pairs. They are paired together with their own conjugate acid or their own conjugate base, depending on which one they are. So if I have two compounds that have the same chemical formula, but the acid of the pair is going to have one more hydrogen, that's what we call a conjugate acid-base pair. So for example, the item we've used already, we have ammonia is NH3, and ammonium is NH4. This is supposed to be a +1. I'll go ahead and correct that. It's NH4 plus. So the NH4 has one more hydrogen than NH3. So this is the base, and this is the conjugate acid. The acid of the pair is going to have one more hydrogen. So in this case, we have H2SO4, or hydrogen sulfate, and we have HSO4 minus. So one of them has one acid or hydrogen more than the other. So which one of these is going to be the acid of this acid-base pair? It should be pretty obvious to you that the one with one extra hydrogen is the one that is the acid. Try one more simple example. We have H2O and H3O plus. So which one of these is going to be the acid? Yeah, it's the one with the extra hydrogen. Hydronium is going to be the acid, whereas H2O is the base in the pair. So now let's look at this equation of a Bronsted Lowry model base, where we have ammonia in water produces ammonium and hydroxide. So it's a Bronsted Lowry model because this does not contain hydroxide in it, but it does produce hydroxide ions whenever it's dissolved in water. So what we want to know is which one's the acid, which one's the base, which one's the conjugate acid, and which one is the conjugate base. So we have acids, we have conjugate acid. We have base, we have conjugate base. Which one is which? The acid is obviously the one that has the extra hydrogen here. We know that H2O is going to be the acid. It's the one that's going to donate a hydrogen. Our Bronsted Lowry model tells us that hydrogen donor is the acid. Well, we know here that the hydrogen, there's two hydrogens here. Well, the NH3 gained a hydrogen, so it definitely didn't donate one. And the hydroxide, remember, water can be written as HOH. So if we had HOH here, then it should be pretty obvious that the OH lost a hydrogen. So it donated the hydrogen, so it is the acid. And since it is the acid, that would make ammonia, NH3, the base. Helpful thing to remember, if you're talking about which one's the acid, which one's the base, they're always going to be on the same side of the equation. The conjugates are on the other side, so the reactants are the acid and the base. The conjugate acid or conjugate base are going to be the products. And again, just like we identified the acid as the one that donated the hydrogen, the base is the one that accepts the hydrogen ion. That's the Bronsted Lowry model, is hydrogen ion donor and hydrogen ion acceptor. The donor is the acid, the acceptor is the base. So now we have to decide which one is the conjugate acid and which one is the conjugate base. Which one is the one formed from the other? So let's look at the acid. We know that H2O is our acid. We've already discussed that. It's HOH, and so it donates its hydrogen. It's going to donate that hydrogen, and it's going to leave us with OH minus. That's this. Now, when the acid donates its hydrogen, what you're left with is the conjugate base. So that means in this situation, OH minus is our conjugate base, because it is what is left over from our acid whenever it does donate that proton. When that hydrogen ion gets donated, then what's left is our conjugate base. When the acid donates its proton, donates its hydrogen, the conjugate base is what's left. So when the base accepts the hydrogen, the conjugate acid is what's left, or what remains. So in this case, my conjugate acid is ammonia plus NH4 plus, because when the NH3 accepts that hydrogen from the water, it forms this. So the acid donates its proton and becomes the conjugate base. The conjugate acid, the base is going to accept that hydrogen ion and become the conjugate acid. And that is basically the way this is defined when we're talking about the Bronsted Lowry model of acid-base, conjugate acid, conjugate base pairs.